not really and there's not so much of a solid base of you have to do this in this situation. You have to do this in this situation. A lot of it is trial and error. So one thing that I want to try and encourage is the idea of just trying to have a go at things. Okay, I mean, a lot of this is driven by intuition rather than theory because there still isn't much of a base at the theoretical level about how these things work. So we want to think about what kind of things we should be considering when we're doing these kinds of implementations. Okay. Right, and one comment I want to make, so all of the slides that I'm going to show, these are going to be publicly available on my GitHub, which I'll give the link, I'll write it on the board later. So you can have access to these later. There'll be snippets of code and so forth that you guys can use to play with. So yeah, I really want to emphasize there's quite a lot of limitations when we're using this kind of framework. I mean, this is a new field. It is rapidly evolving. There's lots and lots of open questions and lots of unsolved challenges. And the kind of things that I'm going to discuss, these are not universally applicable. And as I said, you might change one of the many, many, many moving parts and you get completely different results. Okay, so you have to take everything with a grain of salt. I'll be showing various simulations for illustrative purposes. Okay, I want to emphasize these are not hugely optimized. And as I say, small changes may lead to different results. These are really meant to be illustrative rather than, universal truths. And again, as I said, there's many moving parts when you're using neural networks, and changing one little bit might mean you have to reevaluate everything else. So, I mean, the real first question is why we should be using neural networks to solve PDEs. And if you're solving a single one-dimensional ODE, right, not even a PDE, there's really not much point. Okay, this is one thing to keep in mind. And if you use some kind of classical method, a finite element, finite difference, whatever, these tried and tested, well understood methods, it will probably be much quicker and you'll get much better results and you'll be much more confident in your results. Okay, now there's all different ways that people integrate neural networks, artificial intelligence, machine learning with numerical methods for PDEs. But all of these really, they only have their advantages when they leverage the scalability of neural networks, right? We're thinking of problems that are somehow big or complex. So, I mean, the most classical example is when we're thinking about high-dimensional problems. Okay, so one of the code snippets that I'll be putting up on the GitHub later is looking at like a 10-dimensional Poisson's problem. Now, if we're in a square, say, and you want to use a finite element method or a finite difference method, if you have 10 degrees of freedom in each axis, you're talking about 10 to the power of 10 variables. And this doesn't scale nicely. This is the curse of dimensionality. Even the implementation would become really complicated. But what you'll see in the code that I put up there that we see in the GitHub later is that just by changing a single number in the code, we can go from 1 dimensions to 10 dimensions, and it takes basically the same amount of time to run. Okay, so we're not, even though I'm going to show lots of 1-dimensional, 2-dimensional examples because I think they're easier to understand, really that isn't what the aim is, right? We're thinking about other types of problems. One thing that I'm not going to be talking about in this course, but something to keep in mind, neural networks can learn methods for improving classical methods, right? I mean, it's not just about using the neural network as your solution. They can also try to improve the method itself. And there's been some quite nice recent work where essentially the neural network is obtaining the mesh over which, or optimal mesh, over which you find a finite element solution. So you're still using classical methods, but with a machine learning twist, okay? But this is the kind of thing that people do, which I'm not going to talk about in this course. And one of the big things, and this is really where my interest is when you're learning solution operators for parametric problems, right? You might have a 1 or 2 or 3-dimensional problem, but you have a huge amount of parameters inside your PDE, and this gives you somehow a high-dimensional problem. And the scalability of the neural network can help there. What we're going to see in this course, we're only going to look at a really small little corner of this just to get you guys more familiar with the language and the methods and so on. I'm going to be focusing, as I say, on really simple toy problems. Maybe 90% of the pictures I'm going to show, these are solving second derivative of u equals f. right? Not even a PDE, ODEs. But I think this is enough to kind of capture the main ideas of what we want to get at. So, and the way that I see a lot of these methods is that really whatever you're doing with a neural network, what you're trying to do is approximate some function, right? The function may be the solution itself to your PDE. The solution may be a solution operator, i.e. an operator between some function space to another function space, but these are all just games of approximating functions. Now, there is a general framework which divides itself into 3 steps, which are basically the 3 sessions that we're going to have at the start, the more theoretical ones, where the first thing you have to do is choose some kind of architecture, right? So, okay, there's all kinds of neural network architectures that you can consider. Essentially, if we think of this in a really, really abstract sense, we're trying to approximate a function, we need to discretize it. Okay? What is a neural network? It is just, in my opinion at least, a highly nonlinear parameterization of a function space. Okay, why is it parameterized? So we can stick it in a computer. It has its benefits, it has its drawbacks, but ultimately this is all it is, right? We just find some way of parameterizing a function we want to approximate. Then the next thing that we need to do is define some kind of loss function, right? I mean, all of these machine learning techniques using PDEs, they're basically defined by some kind of optimization principle. We have some loss function if we think of the simplest case of solving Poisson's equation with a homogeneous Dirichlet condition, right? We can think of a loss function like this. We have the Laplacian of our neural network. We take away the right-hand side, we square it, we sum this over various integration points. If this thing is 0 for every single sample of xn we can find, well, this means that the Laplacian of u is equal to f. We solve the PDE. Same on this right-hand side part. If we take points on the boundary and we evaluate something like this, if this is always equal to 0, then we satisfy a homogeneous Dirichlet condition, right? So what we want is that the minimizer of our loss somehow corresponds to the solution, or at least a good approximation of the thing that we want to approximate. Then once we have our parameterization, the thing we want to minimize, I mean, you need to optimize it, right? I mean, you need some kind of optimization scheme. The most typical one is just to use a gradient descent, right? So okay, if we think of theta just being some giant vector that contains all of the parameters which describe our neural network, then we just update it by multiplying the gradient of our loss function by some parameter. Okay, so this would be a simple gradient descent or stochastic gradient descent. Now, as I said, I mean, there's lots and lots of moving parts. You change one little bit, you change everything else. So it becomes very difficult to talk about each of these things in isolation. So for the first bit of this course, I'm going to be talking about architectures, and the second bit losses, and the third optimization. But we can't really talk about architectures if we don't know how it affects losses and optimization strategies, right? So just for the sake of having something concrete in mind, throughout, even if I'm only talking about architectures, I'm thinking of things in the context of solving Poisson's equation in some low-dimensional problem and using a gradient-based optimizer in order to update all of our weights during the training, okay? Any questions up to now? Okay. So as I say, we're going to start with some really, really, really simple problems. Second derivative of u is equal to f, where on the interval 0, 1, we have a homogeneous Dirichlet condition. Okay, we can write this by hand, basically, right? You just integrate it twice and put the right constants in. But through this example, we can see a lot of what happens when we're using neural networks to solve PDEs. Okay? The reason why we consider this, if you want to do a complicated problem, you have to know how to do a simple problem. Right? And I'll try to present this in a way that kind of generalizes further up the chain. So I'll start by talking about architectures. And the architecture that basically everyone uses if you go into the kind of literature around these kinds of problems is a fully connected feed-forward neural network. Okay? What is a fully connected feed-forward neural network? Well, we have a sequence of layers which we compose. What is a layer? It's just a function, okay? A parameterized function. So each layer is just some mapping from some Rn type space to another one where the dimensions may or may not be the same. we have some affine function. So AI is a matrix where the dimensions are correct to make sure that the scaling, the input and output are of the right dimension. So you apply this matrix and then you add some vector. You get another vector in some other dimensional space. Then you apply an activation function. So this is something that you specify from the start. This isn't something that you trained. You just decide, I want it to be whatever function. And it acts component-wise. Okay, so these are typically functions from R to R. And you apply it to this vector just by doing every single component independently. So this activation function is fixed. You don't touch it at any point. You specify it in the first line of your code, and then you just let it run for the rest of the process. But these guys, the matrix and the vector that appear inside the activation function, these are your trainable parameters, okay? Because we know, right, a matrix, this is an ni times ni plus 1 array of numbers, right? We can optimize over it. The same with these guys here, which we call the biases. These are the weights and the biases. And then we just compose a bunch of functions of this form together, and we get a neural network, okay? Typically in this kind of literature, you don't tend to see networks that are that deep, a couple of layers or so. And okay, one thing to comment is that the last activation function, so okay, if we think of this chain of compositions, the last one is LM. So we always take the activation function in the last layer to be the identity. Right? The reason for this is sort of semi-clear. If we have sigma, which is something that can only go between, say, -1 and 1, this limits the expressivity of the output, right? Because the output of this guy is only going to be between -1 and 1. Okay, so it's kind of, it's only affine with respect to the last layer, essentially. Now, why is this kind of parameterization useful? This comes from universal approximation theorems. There's various versions of it. The classical one says, if I have a compact subset of Rn, and I have any activation function which is continuous and not a polynomial, then a big enough network can approximate anything uniformly. Okay? Big enough means either we have lots and lots of layers, or it means that these numbers are really big. Okay? So this is a kind of asymptotic statement. If we have enough parameters, essentially we can approximate anything that interests us. Now, there's all kinds of variations of this result that have appeared in other contexts, and the one that's useful to us from a PDEs community are versions that say you can do similar approximations in, if I say Sobolev norms or HS type norms, things like that. Again, you have the same kind of results. As long as you have a smooth enough activation function that's not a polynomial, for example, you can approximate both the function and its derivative. Right? Now, this is useful if we want to do PDEs. So what kind of activation functions do people use? I mean, if you look into the kind of data science community, the one that you'll see lots is ReLU, Rectivated Linear Unit. What is it? It's just 0 and then linear. Now, this is not a good thing to use for PDEs because it's not even differentiable. Right? If we want to try and solve a second order PDE, this is going to produce all kinds of problems because its second derivative is 0, 0, and okay, we have a delta mass essentially here, which isn't really useful. So for the most part, I'm going to ignore the existence of ReLU activation functions in this course because they're not really useful for us. What's more typical are to use the hyperbolic tangent function or sigmoid function. Okay. Generally, I see a lot more of hyperbolic tangent function than sigmoid. But the idea is that these are both functions that qualitatively have similar properties. They're constant at infinity and smooth and have some transition at 0. Okay. Also, and one thing to note, if we have a smooth activation function, well, if we think of these layers, each layer is smooth. We have a smooth function composed with an affine function. If each layer is smooth, then the final network is smooth. Okay, so your network inherits the regularity of the activation function more than anything else. ReLU is piecewise linear. That means that these layers are piecewise linear, and you end up with a piecewise linear function here if you use ReLUs, right? Now, the first example that I wanted to talk about, okay, this is the effect of size, because something that I've picked up on quite a lot is that you tell people about the universal approximation theorem, and they think, okay, if my neural network isn't training properly, I'm getting bad results, then I should just make the network bigger, right? This is what a lot of people tend to think. It's their gut instinct. Now, theoretically, okay, you can always get a better approximation by using a bigger network. I mean, this is more or less what the universal approximation theorem says. But there's a whole bunch of stuff before you get to this good approximation, right? I mean, it's not just enough to say that there exists a very good approximation over this space. You have to find it, right? And in fact, there's this one work here where what they say is that they can explicitly define problems where they can show the existence of a neural network that can solve particular tasks, but they somehow show in the language of computer science that there is no algorithm that can actually find this approximation, right? So this is something we really need to keep in mind. A bigger network, in theory, may be more capable of approximating the solution, the function of interest, but that doesn't necessarily mean that in practice it's going to be better. Okay. So I'm just going to do a really, really simple experiment where we try this 1D problem with this pins loss. Okay. So as I say, we're only really thinking about the architecture. What we have is we're just minimizing the integral of second derivative minus f squared, and then the same kind of thing on the boundary. We use a gradient-based optimizer in order to try and find the minimum. And what we can see, I'm not sure if you can see well at the back, is that we have all these different widths. So this is just a single layer neural network, one layer where I have either 50, 150, up to, 10,000 neurons in the middle. And we can try and see how the behavior changes depending on the size. So as we go through the training loop, so we have the number of iterations here and the loss at each iteration here, what we can see is that there's all kinds of different behaviors, right? Okay, this one at the very, very top, which is always on the top, this is the largest network. It's the slowest to train at any given moment. When we have other widths in the middle, at certain points they're winning, at certain points they're losing. And what we can think of is, okay, at the end of training, what is the final error that we obtain? And we see this kind of U shape, okay? Now, really, really want to repeat, these kinds of images, these are qualitative, right? These are illustrative. If I did 100 iterations or 100 versions of this and took some average, I would expect something similar qualitatively, but not quantitatively. Okay, there seems to be some kind of optimum zone where if we're too small, we have a limit on expressibility. If we're too big, things are training too slow, right? And then this always happens. If you have a really big network, each iteration is more expensive. So these 1,000 iterations take far longer, and it tends to train much, much slower. And this is kind of related to a conditioning issue, right? I mean, the more weights you have, the worse conditioned the system is going to be, and it's going to take longer to reach its minimum. Okay, so there's always this kind of trade-off where you have to think, how big does my network have to be? And you generally want it to be smaller than what you would think, right? I mean, just going for a bigger and bigger network isn't going to save the day. Another thing worth pointing out from this is that if we look at how many iterations, we have 10 to the 4 iterations, right? And then still our final errors, I mean, these are somehow of the order, I think this is of percentage in the H2 norm. When we're talking about, sort of quite large errors with regards to the solution, right? So this is a very, very slow process. These experiments take 10, 15 minutes or something like that, if I remember correctly. And this is very typical for neural networks, right? I mean, if you have some kind of iterative scheme, each iteration may be of the order of 50 milliseconds or something like that. But when you have to do thousands and thousands of them, this can take a very long time. Okay. As I say, bigger is not necessarily better. Okay. Once we're in an optimization scheme, it may be that there's an increased cost and the things generally go slower once you reach a certain size. as I say, there's nothing which is optimal at all iterations. If I just want to do a really, really short loop and just to get some kind of qualitative estimate of the solution, it might be better to do something. If I want high precision solutions and I'm willing to leave things for 1,000,000 iterations, okay, it may be that a different size is better. Okay. But yeah, in this particular experiment, if we say I'm only willing to do 1,000 iterations, how big should my network be? There's a kind of sweet spot in the middle, which is around 500, which isn't too big, but there's no way of really guessing this a priori, right? I mean, this is all very, very empirical. Similar things happen with depth, but it's a little bit better understood, right? I mean, remember, we can make the neural network bigger in two ways. We can make the dimension or the number of nodes as big as we like, or we can make the number of layers as big as we like, right? We think of this as width versus depth. Now, deep neural networks tend to have problems because you think we have this composition, and when we take the derivative, which is the thing that turns up when we're using the chain rule, these guys on the inside sort of become products that appear on the outside, right? If we just think of the chain rule, you have the derivative and you multiply by the derivative of the guy on the inside. If we have lots and lots and lots of layers, then we can think of this as having something to the power of the number of layers on the outside, right? Now, if we have something like sigmoid, right, which has bounded derivative, then what can generally happen is that this is going to be something in between -1 and 1. You raise it to a big power, it gets really small. Right? So what this means is that when you're taking gradients using very, very deep neural networks, these gradients can become unnaturally small. And sometimes you need them to be big, right? I mean, you might need to change the corresponding weight quite a bit in order to get an improvement of your loss. But the way that this architecture works means that these derivatives are much smaller than they should be in order to correctly update your weights in a gradient training process. So this problem is known as the problem of vanishing gradients, and it does have a converse, which is the problem of exploding gradients, right? I mean, we had the argument was when we use the chain rule, we have something to a power where the power is essentially the number of layers. Now, if this thing is between -1 and 1, it's going to go to 0. If it's 10, it's going to go to infinity, right? So depending on the type of activation function you have, you may have that the gradients get too small and you don't train, or they might get too big and things are really unstable and then they don't train for another reason. So one method that has been proposed in order to try and overcome this is the idea of skipping layers, which I'll make clearer in the next slide, hopefully. And this should try to minimize this effect. Okay, so this is the idea of residual neural networks. So in a classical fully connected feed-forward neural network, our layers look something like this. Right? We have some function, some linear or affine function, and then this defines our layer. Now, in a ResNet, all you do is just add another guy here. So in principle, if the input and the output of the layer have the same dimensions, this can just be taken to be the identity and you don't touch it at any point. Right? If they're of different dimensions, then you need to kind of reshape. So you can introduce some trainable matrix here. And what the idea is that this feeds information from the previous layer into the next one, right? Okay, so if we can think of it in this way, the solid arrows are what goes inside the activation function. And then the plus, you can think of this as just being the identity if all of the dimensions are the same. By adding this term, it feeds this information into the layer afterwards. Right? And then this has some effect of mitigating the effect of vanishing gradients because the information isn't diluted, shall we say, by the activation function. Right? Because it's the activation function that dilutes this information. Okay? Going from here to here is basically a one-line change of code when you're doing any kind of implementation. And we can have a look at how this kind of thing works, right? So again, we're just going back to this really, really simple 1D problem solving u prime prime equals f. I do some optimization problem with some numerical integration. I use a gradient-based update scheme. And we'll see how it changes according to the depth. Right? If we just use the fully connected feed-forward neural network, just with the regular architecture, And in this example, we can see really clearly how the performance is getting worse as we're getting deeper, right? In theory, these things should be better at approximating, but in practice, it's worse, right? And so this is the final error. This is the final loss. And in fact, if we're looking at the loss rather than the error, it's getting far, far, far worse, right? In this case, we see that it's basically stable. Now, once we introduce these skip connections to try and maintain the flow of information, at least up to a certain point, we can see that it still keeps on adding some kind of benefit, okay? So again, the thing I really, really want to emphasize is that, I mean, in theory, you can get a better approximation, but in practice, you need to think a lot more carefully about the kind of size of network that you're going to be using. Are there any questions or comments up to this point? Yes.
So PK is supposed to be 0 at the number.
And so in principle, it could be anything, right? I mean, if we think that what this is doing is trying to preserve information, then it should be sort of like, I mean, some kind of projection, right? So it should be order 1, let's say, right? And if the dimension of the input and output are the same, then you normally just take this to be the identity and you don't touch it. I mean, making it trainable, this is just so that the dimensions are the same, right? I mean, if your input is 3-dimensional and your output is 4-dimensional, then you can't use the identity. Okay. Any more? Okay. So I mean, when we're having talking about the architecture, I mean, we're normally thinking about, you know, how do we parameterize our neural network? But there's a really, really big question about initialization. And all of these optimization schemes are iterative schemes. What do we know about iterative schemes? If you start at a very good solution, then they're quick. If you start at a very bad solution, maybe you end up with absolutely nothing. Right? So the way that we initialize all of these parameters is just as important as the way that we choose to parameterize our network itself. So normally, the way that people take the kind of parameter, their initializations in these fully connected feed-forward networks, these are based on some kind of random sampling. I mean, they're not deterministic initializations. You choose the things according to distributions. Now, if we take TensorFlow, which is the one that I use for a lot of these applications, the default initialization is what's called the Glorat uniform initialization. Okay? So remember, we have this affine map, AKX plus BK. So BK is a vector, AK is a matrix. It takes BK, the bias, to be 0, and AK, the coefficients of this matrix. They're taken independently from a uniform distribution on some symmetric interval, where this constant depends on the size of the input and the size of the output. Okay? So they argue that if you do this in a certain way, in this particular way, should I say, and if you're using a hyperbolic tangent activation function, then in some statistical sense, this initialization preserves the flow of information through your network. Okay, it's a kind of, I mean, they make it much more rigorous in their work, but this is the argument, right? If they're too small, then there's no information. If they're too big, then there's too much information and everything's just noise. But having this kind of scaling means that the information flows well from one layer to another at the initialization. Now, this is general, well, this is used quite a lot, but all of their arguments really are based on when you're considering a loss function, which is kind of like an interpolation problem, right? I have my neural network, I have sampled inputs, I have sampled outputs, and I want to find some kind of regression type approximation to this data. When we're talking about solving PDEs, our loss functions involve derivatives of the neural network. And it's not really clear if these arguments hold once you're talking about this kind of problem. Right? But people still tend to use it as the default because it's just the easiest thing to use. So what I've done in this experiment, again, we're just doing this really, really simple one-dimensional problem, solving u prime prime minus f is equal to 0. And I'm doing essentially the same kind of initialization. I take these vectors bk to be 0, and I take the coefficients of this matrix to be uniformly sampled on the interval -a, where now I'm varying this parameter. Okay, so we can think of this being very, very small initial weights or very, very big initial weights. Okay, if, for example, a is 0, then we're initializing these matrices to be 0. If we do hyperbolic tangent of 0, we get 0, right? So our neural network is 0 at the start. If it's very, very big, then we can think we're doing something like hyperbolic tangent, very big number times x. So we have very, very sharp interfaces appearing in our initialization. What we can see here, again, is that we have some kind of U shape, right? And I think maybe the most interesting one is this solid blue line here. So this is when A is really, really small. After 10 to the 4 iterations, it has not moved at all, right? Essentially, qualitatively, all of our weights are so small that our neural network is basically 0. And there's a kind of symmetry here, right? I mean, if all of the nodes are 0, then there's no preferred direction. This makes it very, very difficult to train. Right? It just kind of sticks there. And what I've highlighted in red here, so this is the A that corresponds to the GLORA initialization for the problem with the size of the network that I've chosen. Why it breaks this kind of U shape? Okay, this is probably just the very, very particular case that I chose. If I did an average over 1,000 simulations, it might be smoother. But the thing to bear in mind is that it doesn't appear to be the optimal one, right? The optimal ones are of these sorts of orders of magnitude, which is 1, right? Whereas the GLORA initialization is closer to 0.1. Okay. Now, one big thing that I really like to emphasize with initializations is that there's this typical thing where they take these biases, the BK, to be 0. Okay, most of the classical initializations do this. Now, this introduces, in my opinion, a very, very big problem, because most of these activation functions that we consider, okay, I'll call these features, they all exist at 0. Okay, if we think of a ReLU, it's 0, this is boring. At 0, it becomes linear. Linear things are boring, but the transition, the thing that makes it interesting, this is exactly at x is equal to 0. Okay, hyperbolic tangent, okay, at infinity it's constant, at -infinity it's constant. These aren't particularly interesting, but the feature, the interface, this is near 0. Okay? This is common for basically all of the main activation functions that people use, that it is uninteresting at the extremes and interesting at 0. Now, if we think of a layer where we have some activation function that's only interesting at 0, well, what that means is that if we think of one component of this kind of affine map, well, all of the interesting parts of this particular function are going to be on the hyperplane where these components are equal to 0, right? We can think each component of this vector defines some hyperplane, and this is where our neural network is going to be expressive. It's where it's going to be interesting, right? Now, if we initialize all of these BKs as 0, that means that all of these hyperplanes are going to go through the origin. Okay? And this seems to be something which really, really limits the expressibility of our neural network. So we can see the kind of effect that we have just by changing a sort of effective bias that we have here. If I offset my neural network by some parameter, okay, so we think that we're in a one-dimensional domain, I take 2 copies of my neural network. One is the neural network itself, and in the other one, I just shift the input by some particular number. Okay, this is the same neural network as far as the architecture is concerned. Effectively, the only thing I've done is change the initialization of these weights. Okay? Now, if we compare essentially this neural network with one with a different offset, we can see a really, really huge difference in the way that things are trained. Okay, so we think of this problem here. So we have, again, really simple problem. Second derivative of u is equal to f. 0 boundary conditions on -0.5, 0.5. And all I'm going to do is solve this problem with a sort of standard initialization. And then I'm going to offset my neural network, which just means moving all of these hyperplanes to, what was it, 10. Okay, so what this means is that these initial hyperplanes in one case are going to be right in the middle of my domain. And in the second case, these initial hyperplanes, which, okay, we're in 1D, they're points, these are going to be way outside of my domain. Okay? Nonetheless, these are still essentially the same neural network. It's the same parameterization, just with different initializations. What's the difference? One of them behaves more or less like you'd expect. Okay, this is really, really typical for neural networks. On a log scale, it isn't doing anything for a while and then suddenly, whoop. This is the case where all of these hyperplanes, which are just points in one dimension, are right in the middle of the domain. If we do this case where all of the features are outside of the domain at initialization, nothing happens basically, right? I mean, we get like a very, very slight decrease, and then it's just flat. My error stays of the order of, what is this, like 10 to the minus 0.5. Okay, this one simple change completely destroys the ability for our optimizer to do anything useful. And this kind of makes sense if we think of a tangent, a hyperbolic tangent activation function. By having this only feature 10 units away from our domain, my neural network is basically a constant. Right? And then, okay, if I basically have a constant, the only thing I can do is raise it or lower it. Right? I mean, it can't see the ability to capture interfaces because it's too far away from the domain. So we can think of this kind of picture. I mean, this is what a lot of the standard initializers do. If we think that we have our domain is a box like this, well, the origin is somehow a special point. Okay, all of these features, which we can understand as hyperplanes. In the case of ReLU, this is where we have transitions in a piecewise linear function. We think of hyperbolic tangent. These are interfaces between two constants. And all of them pass through the origin. If our domain is something like 0, 1 squared, then what we can see is that, for example, this hyperplane isn't in the domain. It isn't particularly useful. Right? I mean, this makes training much, much harder. This is a bad initialization. So one idea, which I find to be very, very nice, this comes from Sear and other authors. What they did was decide a particular type of initialization, which is quite straightforward to conceptualize. When we're doing PDEs, we have a domain. Right? If you're doing something in data science, I mean, the data is somehow very abstract. It's very unstructured. If we're solving a differential equation, we have some domain and we know what it is and we can look at it, we can probe if points are in it and so on and so forth. So what is their idea? So we first take some points, pk, inside our domain. Okay? I'm just thinking at the level of a single layer neural network. You choose some point at random in your domain. Let's say it's this point here where the pointer is. Then you choose nk, which is some random unit vector, right? And then you can consider the plane, which is orthogonal to nk and goes through pk. And what this does is this gives you all these kinds of hyperplanes, which are in a random way distributed through your domain. Okay. Then you can stick some well-chosen constant before it. I mean, they have some auxiliary optimization problem for this constant, but I won't think about this. And then you just think of all of these different scalar problems, right? And if we just think of these as being 1D, and then you do a bunch of copies of this, one for every single node of interest, right? And then what this gives you is this kind of initialization where you have all of these features, these transitions, the points where the neural network is actually doing something interesting tend to be much better distributed throughout your computational domain. Okay, of course, this is very dependent on our kind of applications where we're thinking of a well-defined computational or physical domain. So they based all of their work on the use of ReLU activation functions, but I find them to still work very, very nicely, even if you're using other activation functions. Okay, I tend to use for basically everything hyperbolic tan or sine, which I'll discuss later. And this isn't exactly their method, right? But this is very, very similar to their method. It's in the spirit of their method. And okay, keeping in mind that this is on a log-log scale, okay, the kind of thing that I see in this picture is that not only does it start to drop, reduce the error or the loss quite a bit earlier, but at the end of training, it's still getting better. right? And you can kind of almost understand this. If I have one feature which is vaguely defined, outside of my domain, and it stays outside of my domain for the whole of training because it has no reason to see what's happening in the domain, that's kind of lost information, right? I mean, this is computational power, this is expressivity that I'm not taking advantage of. But when you're using their method, at the very least at the start, every single node is doing something in your domain. So in a very hand-wavy sense, you can understand that this might make things better at the end of training and not just at the start of training. Now, exactly doing their method involves some auxiliary optimization problem to obtain these constants beta k. But even a very ad hoc version, which is spiritually similar to their work, I tend to find quite useful. But the easiest thing that I always do, okay, whatever I'm doing, is just offset my neural network. Okay, if we think back to this picture, if my domain is 0, 1 by 0, 1, then all these hyperplanes go through the origin. Well, if I just shift my domain, now the origin is in the middle. Right? This is not even a one-line change of code. Right? I mean, all I do is I define my x0, which you could take to be the center of mass of your domain, for example. Then you just put in your first line of code where you're defining your architecture, minus this number, and this tends to work much better in my opinion. Right? It's the simplest change without having to think too much to overcome this issue. Of course, better things can be done. Are there questions or comments or anything up to this point? Okay.
Is there a way to start from the origin to have the loss function of term that gives you inside the domain eventually, and then
I would just think of this as being, I know what my domain is, I know what its center of mass is, so I can just put this inside the definition of my neural network, which is just changing the parameters a little bit. And I mean, if we go back to the definition of, I'll be back. Okay, we're back online?
yes.
Okay, excellent. Okay. With the technical, okay, so I'm this idea of trying to distribute features through your domain. Okay, this is kind of easy when we're thinking of the idea of something like ReLU, hyperbolic tangent, so on and so forth, which are basically uninteresting, transition at zero, uninteresting again. Now, one particular idea that I find to be very, very useful is what's called the sirens initialization. Okay? So the main idea is that we use a sign activation function. Okay? The big difference between something like sine and something like hyperbolic tangent, and sine continues to be interesting forever, right? And hyperbolic tangent is only interesting in one place. So what we can think of, if we look at all of these parallel lines here, if we have a single layer, something like this, where now my sigma is a sine function, if we say where it's equal to zero, this is where it's interesting. Not only do we get one feature that appears inside our domain, but we get all of these parallel lines throughout our domain where it's constantly varying. Okay, if we think at the level of a single layer neural network, okay, maybe it might be helpful to write here, then our output is going to be something like CI AIX plus BI, right? This is kind of like a Fourier series, right? Or Fourier transform. So the idea of the sirens architecture, at least the way that I see it, is that if we just think of a single layer neural network, we're kind of being inspired by trying to take a kind of rich, in some sense, Fourier representation of our solution at the initialization. Okay? So we have some kind of sign activation function, but instead of these glorate type initializations that typically take these weights to be very, very small, in this case, we want these weights to be such that we have several wavelengths throughout our domain. Okay, we think of this as a kind of almost initializing like a rich Fourier representation. Now, they extend this idea to when you have deeper neural networks. Okay, the Fourier analogy makes lots and lots of sense if we think of a single layer network. But now if we put this inside a sign function, okay, now we're in some horrible nonlinear world, which is much harder to understand. Okay? So what their idea is that once we go into the second layer, we should be using very, very small weights. And then what that means is that once we put this inside a sign function, well, since we have small weights, we have the classical approximation of sign. We basically get the input out again. So even if we're not gaining structure, we're not losing structure, right? I mean, you can think if we have some really silly idea, if we have a beautiful first layer, and then my second layer has a constant activation function, I lose all of my information, right? I mean, I have loads of expressibility, and then my output ends up being 1 because my activation function is constant in the second layer. So by taking these small weights, at the very least, we preserve the structure at initialization, and then we hope that the optimizer makes this even better later on. Okay? And one thing that I think is really interesting about these kinds of neural networks that I've never really understood if it's helpful or not, but I think it's very interesting. If we have a neural network of this form, so it's a composition of signs with these parameters in it, affine weights, and so on and so forth. If you take its derivative, I mean, you can almost write by hand what the chain rule gives you in this case. And by playing around with a bunch of trigonometric identities, you can show that this is equivalent to a different neural network, but with more or less the same structure, right? It's still going to be a composition of signs with affine mappings and signs and affine mappings and so on. Maybe you have to write it in a slightly different kind of way. I mean, maybe it will have the same number of layers, but it might have more nodes and so on and so forth. But in some sense, it preserves the structure. Now, this is very, very different to when you have something like a ReLU network, right? If you have a ReLU network, then your network ends up being piecewise linear. You take the derivative, you get something which is piecewise constant. Right? You've completely changed the structure by taking the derivative. But with these kinds of architectures, I mean, you preserve the structure with derivatives, and I'm convinced there's something deeper going on there that I've yet to get my head around. Right? So again, showing a very simple little experiment that I did with these guys. So I took a slightly oscillatory solution. I mean, it's nothing crazy, but it's still 1D. And comparing with a hyperbolic tangent activation function and the standard Glorot initialization versus this sirens approximation, I mean, we see a huge difference in the behavior. Right? I mean, the sirens one, I mean, it gets very, very small, very, very quickly. The other one is basically stagnant, drops, then starts improving later. And as well, I mean, this is something where if we think, okay, this is going to be much better at approximating oscillatory solutions. And then this is a kind of general thread within this kind of work is if you know information about your solution, then you should try and incorporate it into your architecture. If I'm trying to solve something which has oscillatory solutions, then maybe I should be putting in an oscillatory activation function. Okay? And again, this slightly oscillatory problem. Now, there's one thing which we can kind of qualitatively conclude from here, is that the tanh activation function isn't doing a good job of approximating it. Now, this is something which is well known, which I'll talk about in the next session, which is called the F principle, which basically says if I have a standard neural network, it's generally very good at approximating low frequency components and very bad at approximating high frequency components. And this happens especially when you have these kinds of sigmoid tanh activation functions. I mean, they struggle to approximate things which are high frequency. But again, if we know we have an oscillatory solution, why not make our neural network as oscillatory as possible? So a few things I really want to emphasize. Okay, so going for a really, really big neural network is normally not the best idea. Okay, whilst in principle, it may be the case that you have a greater approximation capability. But in practice, okay, the big first thing is that it makes the training expensive. If you have several layers, then what you have is a matrix in the middle, which is number of nodes in the layer before times number of nodes in the layer after. So this is kind of quadratic growth in the number of nodes that you have. So this gets very, very expensive very, very quickly. And it might seem, even though each iteration is more expensive, you might also need more iterations. So I mean, this is something that you see all the time, that it seems to be some kind of conditioning problem where bigger networks are more ill-conditioned and they take longer to train. Where when I say longer, I mean number of iterations, not just cost per iteration. Another thing is that you can make really, really simple changes in your architecture, and these can make really, really significant gains when you're training. Let's say, I really want you to think about this example where I just took exactly the same network, I did an offset by 10 units, and it became absolutely useless. Okay, just one, not even a one-line change, 3-character change, right? If I wrote in the first line of code defining my neural network, input equals x minus 0.5 instead of input equals x, right? I mean, this already completely changes the behavior of the training. And I think initializations are something that people don't think about as much as they should. I mean, having a very good initialization can mean the difference between converging in very few iterations or maybe not at all. Again, thinking of this really, really simple offset case, in 10,000 iterations, it did absolutely nothing. Okay, and this is just, again, a one-line code, one-line change of code.
But when you say it does not, means that the loss function is oscillating back and forth somewhere?
I know, which one was it? It was this one. I mean, okay, it goes down a bit. I mean, it starts sort of order 1, then it gets to order 0.5 after 10 iterations, and then that's it, right? I mean, there's absolutely no improvement in the loss. If we look at the error, I mean, okay, this is log, this is 10 to the 2, this is 10 to the 3. I mean, it's essentially doing nothing. I mean, the noise which you see here is because there's like a Monte Carlo integration thing there, which makes it a little bit noisy. But I mean, it's a little bit noisy and it's essentially doing nothing. I mean, if you plot the solutions in this case, then what you have is that it's basically just a constant, and then it tries to make the best constant to solve the problem, which is useless. Yep. We're done for time. Are there more questions? Yep. Yes, so then you have stochastic and stochastic, right? I mean, the initialization is typically stochastic. And then later, I mean, I've been sort of glossing over this bit of it, but I mean, this is very key. I mean, this integration is also going to be stochastic, right? I mean, if you use, I'll talk about this in the next session, but if you use fixed integration points, things can go really, really badly. So you have, I mean, there's a lot of variation in these problems, which comes from the stochastic part. I say if you can exactly evaluate your loss and the gradient, yeah, I mean, this would still have an effect, right? I mean, if we just consider the case of something like this isn't even going to be a neural network, right? This is just going to be tang x minus b, right? So I have one trainable thing, and my loss, no errors, no integration, nothing like that. Okay, this is going to be ubx. And I have something like my loss is ub at 0 minus, just ub at 0 squared, right? Now, if I start with b really, really big, then this is going to basically just be, b is really, really big. So this is going to be like what, minus 1 squared, which is going to be like 1, and its derivative is basically going to be 0. Okay, so I need loads and loads of iterations to make this b, which is really big, the derivative is really small. I update with this tiny derivative that doesn't really do anything, and it takes forever, right? Whereas if I'm near the optimum value, which would be, 0, then this is basically going to be b itself, right? So, I mean, it changes everything with or without the stochastic part. Yep.
So, there are several different ideas, but there is another part of the group that you can out.
Is this in the context of like database problems? Because there's a different situation there that I've seen.
That's a very different format, the model complexity. That there are papers so that maybe even making the model more complex, in the end, it became part of the model.
So if I think I know what you're talking about, so there's a picture that I've seen quite a lot. So if we think of an interpolation problem, right? So I have inputs and I have outputs and then some data, and I just want my neural network to make a good interpolation of this data. A picture that well, at least I've seen quite a lot, is that essentially if this is the number of data points, right? And sorry, this is so this is the number of variables, right? Number of trainable variables. And when this is more or less equal to the number of data points, then the model performance goes something like, how does it go? So okay, this would be the final training error. And then it goes something like that. And then afterwards it goes like that. Right? Is this the kind of picture you mean? Yeah. So, okay, this is something which is much more related to data-based problems. Now, this is something I'll discuss in the next session. We have infinite data, right? I mean, we're using some kind of stochastic integration scheme. So our n data is infinite. So, I mean, it's qualitatively quite a different story because of this. Because, I mean, essentially what's happening here is you get really, really big overfitting, more or less. And I mean, if you use stochastic integration, you can kind of forget about the possibility of overfitting. Okay, you need some kind of metric to make sure you're converging to the right thing, but overfitting as such shouldn't happen if you do it correctly. Okay, so I mean, this is somehow a data problem rather than a PDE problem. How do you mean? Yeah, and I wouldn't be surprised if strange things happen once you start getting into really big networks, right? But I mean, one of the big things is, I think, to keep in mind is that, I mean, this is a finite iteration scheme, right? If I left this for another and for 10 to the 5 iterations rather than 10 to the 4, okay, it looks like this green one's already sort of reaching its optimum while the blue one's getting better, right? So I mean, in practice, anything can happen basically. Questions, more comments?
There are comments from the chat.
Okay.
Are there any comments from the chat?
This was more or less the time to accept it's a good breaking point just before talking about loss functions. Yeah.
Okay, thanks. We will now have a break and we will resume at the 12:30 or something, some minutes.